Hi, I'm Anton, and it's an honor for me to speak about our work on structured prediction theory with calibrated convex surrogate losses. Structured prediction is a subfield of machine learning which includes the tasks of predicting structured objects. Examples of such tasks include image segmentation, where given an image one needs to assign a label to each pixel, and handwriting recognition, where one needs to recognize each element of a sequence of symbols. For the moment, there are many practical methods for structured prediction, but theory is not well developed compared to, for example, binary classification. In this work, we focus on theoretical aspects of structured prediction and provide some insights how to build methods with guarantees. In particular, we want consistency guarantees, meaning that in the limit of infinite data and number of iterations, the method optimizes the right quantity. Second, we want connections to the complexity of the actual learning algorithms. Our guarantees will give a bound on the number of iterations and samples needed for the learning algorithm to get a generalization error with an epsilon of the optimal prediction function. In structured prediction, we usually want to minimize the population risk, which is the expected loss of the predictor. There are two key differences from the standard binary classification settings. First, the number of possible predictions or classes is very large. If we are talking about sequences, it's exponential in the sequence length. Second, the loss influences a lot how a method should behave. Not all mistakes are equally bad. We cannot get guarantees for the population risk directly because it's non-convex, so we have to use a convex surrogate objective. Example of such convex surrogates include structured support vector machine and conditional likelihood. In this paper, we use the classical notion of calibration function to connect the surrogate and population risks. We also use stochastic optimization to get a bound on both the number of iterations of the learning algorithm and the number of samples needed to learn at the same time. In our analysis, we carefully trace exponential constants and make sure they don't silently appear in the bounds. Our approach allows to get the following results. We get a complete picture for one simple family of surrogate losses, which we call quadratic surrogates. In this setting, we study the role of task losses for possibility of efficient learning. It appears that with the full flexibility of label scores, we get exponential constants in the rates of most of the losses, which means that learning is hard. However, with a special choice of constraints, some losses become much easier. For example, the block 01 and Hamming losses. Being low rank appears to be necessary but not sufficient condition for being easy. By the way, the standard 01 loss is the worst possible case and is always very hard to learn with. In some cases, these constraints even break consistency for small loss values, but make learning exponentially faster after a certain point. If you are interested, please check out our paper for the exact results and techniques we used. We are looking forward for the community to look at other surrogate losses and other possible sets of assumptions. Thank you very much.